Question: does 1 equal 0.9999 to infinity? Common sense tells us that if we are working to n decimal places, that rounding up n plus 1 decimal places of 9s to 1 is arithmetically sound, but this is not what this question asks. Our first task is to define precisely what equals means. 2n equals 2n. 2n plus or minus 1 equals 2n plus or minus 1. But 2n plus or minus 1 is not equal to 2n even when n is infinite. That is to say that even equals even and odd equals odd, but even is not equal to odd even at infinity. To divide a whole into 3 parts, first shape it into a square. Then divide the square into 4 quarters. Divide and give a quarter to red, blue and yellow. Quarter the remaining quarter. Divide and give a 16th to red, blue and yellow. Quarter the remaining 16th. Divide and give a 64th to red, blue and yellow. Quarter the remaining 64th. Divide and give 1/256th part to red, blue and yellow, and so ad infinitum. We have generated the infinite numerical series 1/3 equals a quarter plus a 16th plus a 64th plus a 256th plus a 10/24th. Algebraically, 1 over n is equal to the summation between x equals 1 and infinity of the reciprocal of n plus 1 to the power x, and is true for all integers n. 1/9 equals 1/10 plus 1/100th plus 1,000th plus 1/10,000th plus 100,000th and ad infinitum, and 1 is equal to 9 over 9 is equal to 9/10ths plus 9/100ths plus 9,000ths plus 9/10,000ths plus 900,000ths ad infinitum. It has been demonstrated geometrically that the representation of a rational as an infinite fraction which can then be converted to a decimal fraction will always entail a small quantity, alias the residual, which is equal to the rational minus the partial sum of the series, and is not a part of the representation. So by the definition given in 3, the infinite decimal fraction 1 equals 0.9999 is only an approximation and not an equality. QED. To many, the fact that the infinite expansion appears to vanish into the corner of the square may seem to be incongruous from our parochial viewpoint, but mathematically the square may be an infinite object. Multiplying each term in 14 by 3 to give 3 over 3 equals 1 is equally as valid as 9 over 9 equals 1 in 16, even though the latter gives a decimal fraction of all 9s, and 14 gives infinite 9s followed by infinitely many other digits. Only the rate of convergence is different. If in the formula given in point 5 we put n equals 1, we get what I shall call the fundamental infinite series, which is 1 equals a half plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64th is equal to a half plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th plus 1 over 2 to the 5th plus 1 over 2 to the 6th, and so on. We showed in 14 that 1/3 equals 1 over 2 squared plus 1 over 2 to the 4th plus 1 over 2 to the 6th plus 1 over 2 to the 8th plus 1 over 2 to the 10th plus 1 over 2 to the 12th, and so on, which if we subtract from the series for 1 gives 2/3 equals 1 over 2 to the 1 plus 1 over 2 cubed plus 1 over 2 to the 5th plus 1 over 2 to the 7th plus 1 over 2 to the 9th plus 1 over the 2 to the 11th plus, and so on, which can be confirmed numerically. It is easily seen from the above fundamental infinite series that a half equals a quarter plus an eighth plus a 16th plus a 32nd and so on. A quarter equals an eighth plus a 16th plus a 32nd plus a 64th and so on. 1/8 equals a 16th plus a 32nd plus a 64th plus a 128th and so on, and the rest are similar. Gathering like terms, the modified fundamental infinite series is 1 equals a quarter plus 2/8 plus 3/16 plus 4 32nds plus 5 64ths plus 6 128ths and so on. The series can be expressed at each step as the partial sums a quarter, 4/8, 11/16, 26 32nds, 57 64ths and so on, and the differences between numerator and denominator is 3, 4, 5, 6, 7, 8, 9, 10 and so on. Hence the formula for the partial sums of the modified fundamental infinite series is given by partial sum is equal 2 to the power x plus 1 minus x plus 2 all divided by 2 to the power x plus 1 for x equals 1 to infinity. This is counterintuitive because as the size of the additional terms of the series get infinitely small, the difference between numerator and denominator of the partial sums becomes infinitely great. The formula for the partial sums of the original fundamental infinite series is partial sum equals 2x minus 1 all divided by 2x. The fundamental infinite series converges only slightly faster than its modified series, generating approximately x divided by 3 leading 9s. This has been checked for x up to 1000. We have slowed the race to infinity down. Wow! The infinite series for 1 equals 0.9999 can also be slowed down in similar manner. If it was truly equal to 1, that would not be possible. QED. Unlike true incommensurables like root 2, which cannot be terminated at any stage of the expansion, decimal fractions can be halted at any time. If you look up Zeno's paradox by Numberphile on YouTube, you will be told that 250 years after Leonhard Euler and 17 years into the third millennium, at 6 minutes 20 seconds into the video, that infinite series are still a paradox. Yet in the 1822 edition of Euler's Elementary Algebra, on page 93, we find the following footnote. It may be observed that no infinite series is in reality equal to the fraction from which it is derived unless the remainder be considered. Welcome to the return of the Dark Age. This slide gives examples of rational fractions which are just reciprocals of the integers, expressed as simple infinite series and applicable to the infinity of the integers. Every series can be multiplied by the denominator of the fraction they represent to give every series claiming to be equal to 1. So if 1 equals 0.999 to infinity, does this mean that all the upscale series are therefore all exactly equal, or is there just one prime candidate? If so, how would we know which infinite series it is? since we only have access to a finite number of leading 9s. Construction of all series is self-evident, and the rule for obtaining the denominator of the fraction is to subtract 1 from the base number of the power term and multiply by the constant term. So the fraction whose first term is 1 over 4 to the power 1 times 5 is 4 minus 1 times 5 equals 15. So the fraction is 1/15.